Hello, I'm Mrs. Weller. I teach AP Chemistry at the high school, and today some of my students are here to show you some chemical demonstrations. Sit back and enjoy. I hope you have a good time.
This demo deals with a sublimation, and sublimation is basically the change of phase from solid to a gas not going through the liquid phase. And a perfect example of sublimation is dry ice. And in here I have some water and soap, and I'm going to add some dry ice, which is solid CO2 in here. And as you can see, it just bubbles into gas, not going into the liquid stage. And this is just gas and bubbles. And in this one, I have water and some universal indicator, and it changes the water to green because that's neutral. And I have some KOH, which is a base. I'm just going to add it to this. Watch for the color change and it to change blue. So now it's basic. When CO2 is dissolved in water, it changes the pH to slightly acidic. So I'm going to add some dry ice into this, and it should change color again. See, it's now changing green, which is neutral, and then it's going to change into yellow. And this is just steam. Okay. That's it.
All right, I have some acetone, which is the same type of thing that's used in nail polish remover. So I'm going to put this normal styrofoam cup in, and I hope you can see what happened. There's air bubbles coming out, if you can see it, and those are the air that's in the cup. And what's being left, once it's finished, all that's left is the polystyrene, which is what we call styrofoam. It's a type of plastic, a polymer. So this type of thing is used, and you can see this is what the cup was. And now if we let that harden, it would be just like normal plastic, kind of like what's in the same type of things used in toothbrushes and CD cases. It doesn't have the air, but it's the same type of plastic.
Okay, my demo is called the dust explosion, or grain elevator explosion. This paint can represents an elevator full of fine powdery grain, and inside it I've put lycopodium powder, which is actually a fine powder made from the spores of a fungus, and it's explosive. Now I'm going to introduce a flame by lighting the candle inside. And now when I disperse the powder into the air and blow it into the flame, you'll see an explosion. So the reaction that's happening is a chemical reaction called combustion. And when the reaction happens very fast, it's called an explosion. The reason the reaction happens so fast is because the powder has a lot of surface area. Each tiny particle is surrounded by the air that it's reacting in. So we got a fireball. And that's why sometimes when there's a spark or too much heat in a grain elevator, there will be an explosion.
What happened here was I had a soda can on this hot plate, and I poured water into the soda can, and inside the can the water started to boil. And when it boiled, the vapor from the water took the place of the air inside the can. When I took the can and flipped it over into the bath of ice, all that vapor that was inside of the can condensed out to the sides of the can, and the pressure from the outside air crushed the can since there was very little air left in the inside. So you'll see it again. Works every time. Do it again for us. Once more.
Here.
All right, you're on, Heidi.
Let's
Hi, I'm doing what's called the old Nassau clock reaction, and I want to just preface this by saying I'm the only person in the world who can do this. Other people have tried, but they can't do it as well as I can. So what I'm going to do is I'm going to take these two clear colorless solutions, which I mixed up ahead of time. I'm going to pour this one into this one, and it's going to turn a magic color. Watch closely. Ooh. Now, I have my volunteers, Zach and Doug. Zach, would you come up, please? Okay. You can try to do this like I did it. All right. Same stuff. They're both the same reactants, and this is the same thing you're going to pour it into, so give it a shot. Make sure you hold it so everybody can see it. What did you do wrong? Well, as you can see, he didn't do it as well as I did. So, there's somebody else who thinks they can try it. Here you go, Doug. Make sure you hold it so everybody can see. Shake it around. Ooh, you got the orange too. Wait a minute. Now, how did that happen? Thank you. Okay. As you can see, we've got a few different reactions going on in these bottles. They are all the same chemicals that we added together. They're just in different concentrations. There's different amounts of each chemical. So in this first reaction, there was one reaction which produced an orange color. In the second reaction, there was a different reaction, but it produced a black color because there were different concentrations. But in this third reaction, both reactions took place, so the orange and the black both occurred. And it's called the Old Nassau Clock reaction because Princeton colors are orange and black, and Nassau Hall is a building in Princeton. Set.
Heidi, you're on.
Okay, we're going to have an experiment here. It's called chemiluminescence because, well, you'll see why it happens. Whatever. So we're going to just pour this. This is some peroxide, and we're just going to pour it into here, which has some solution. Is it working?
Yep. Okay. As you can see, the solution is glowing by itself. This is called chemiluminescence. It's when a reaction occurs which gives off heat in the form of light.
So, like the other reactions, instead of giving off heat, it gives off light. So that's why we call it that.
It's an exothermic reaction. This is the same kind of chemical that is used in glow sticks that you might carry around on Halloween.
And the same type of thing that's found in fireflies, which is the reason they glow up too.
Yep, that's it.
I'm Brett Carpenter, and I'm going to show you a little demo with liquid nitrogen. Now, liquid nitrogen is below negative 200 degrees Fahrenheit. So, as you can figure out, it's pretty cold. We're going to show you what this liquid nitrogen will do to a couple common everyday materials. Now, in here, we have balloons. And I'm going to show you what happens to these balloons when they've been exposed to these temperatures. You can see how this one here So as you can see, the balloons are actually inflating. And the reason that's happening is because what we call ideal gas law. And that's when a gas shrinks when the temperature plummets. So as we take it out of the liquid nitrogen, the temperature, of course, is increasing because this is room temperature. And so the gas is expanding to what it was before we put it into liquid nitrogen. We've also got these flowers here. And we're going to see what happens to the flowers when we place them in liquid nitrogen. Now you can, I don't know if the mic picks this up, but the liquid nitrogen actually boils when we put the flowers in. Now the reason that happens is because the flowers, again, are at room temperature. So when we put it into liquid nitrogen, the liquid nitrogen is actually boiling because it's above its boiling point. So we'll let that cool. As you can see, it's very brittle now. It's no longer pliable. We'll try that again with one of these. Just one more time. Again, very brittle. Now what we've done is we've put a racquetball in this liquid nitrogen. And we're going to see how the racquetball responds to these extremely cold temperatures. I've got one right here. See, it's frozen. This one happens to be a Wilson. And you just stand back. We can see that this racquetball, when it was frozen in liquid nitrogen, is no longer pliable. In fact, just crush it like that. And it will return to its normal temperature. It hasn't been harmed, but again, it's just been made very brittle. Thank you.